Hi everyone. So in this video, we're going to run through some MATLAB code that I wrote for signal processing of surface electromyography or SEMG signals. Now, if you haven't checked out my previous video on the general steps to follow when processing surface electromyography signals, do check it out by clicking the link up here. If you guys like this video, don't forget to give me a thumbs up by clicking the like button below, and if you haven't done so already, please subscribe. I'm Chums, and welcome to ThatsEngineering. Alright, so this is the MATLAB script that I wrote for SEMG signal processing. Now I will run through the sections in this script to give you an understanding of the steps I performed when analyzing SEMG signals. So first of all, I cleared the workspace, and in the first section I obtained or imported the raw data from the sensor or the data logger. So if you saw my previous video, I used a biosignals Plux data logger, and I can obtain the digital readings from that data logger as a text file. So I imported the text file into MATLAB using DLM read. I also pre-allocated two variables, one to store the data and one to store the time values. So I'll go ahead and run this. And in the second section, I just assigned the time values to that particular variable. Right. So in this section, I used the transfer function of the biosignals Plux data logger to convert the digital values in the text file to analog voltages which represent the actual electromyography signals. So the transfer function is given here. Keep in mind that depending on your setup, you would have a different transfer function. I multiplied the final product by 1000 to obtain the readings in millivolts. So I'll run this. Right, so just for your information, I had 3 channels, each channel representing a muscle. So the first channel was for the tibialis anterior, the second for the gastrocnemius lateralis, and the third for the medialis. And over here, I plotted the raw SEMG data, which is the original SEMG signal obtained from the data logger. Now I'm pretty sure I don't have to explain how I plot it, but just for your information, I used a for loop to iteratively subplot the 3 channels on a single figure, each channel for one muscle. So I'll go ahead and run this. And this is what the original or the raw SEMG signal looks like. So you can see there's a lot of noise and a lot of distortion. Okay, right. So due to the noise and distortion in the raw signal, the next step was to implement a filter. But before that could be done, the cutoff frequencies for that filter had to be decided. And this was done by performing a fast Fourier transform or FFT. The sampling frequency was 1000 Hz. And using that, the FFT frequency range could be calculated in this line. By definition, the FFT frequency range is the frequency resolution from 0 to half the data length. So this section involved calculating and plotting the FFT. The FFT can simply be found for a data set using the FFT function on MATLAB. And this would give you the two-sided or the double-sided spectrum. The absolute value of that can be taken and then divided by L for normalization of the output power with respect to the length of the input signal. That's in this line. And the next 2 lines were used to compute the single-sided spectrum. So what you do is you take the positive part of the double-sided spectrum and simply multiply it by 2. The rest of the commands were there to plot the fast Fourier transform. So I'll go ahead and run this. And you will get a plot similar to this. So this is the FFT plot. It shows the frequency range along with their intensities. So as per my previous video, the cutoff frequencies were set at 30 and 300 Hz. So everything beyond 300 Hz is mainly due to high frequency noise, which will be filtered out. And everything below 30 Hz is mainly due to movement artifacts, distortion caused from movement artifacts, which also have to be filtered out. But like I mentioned in my previous video, these values are not standard, So they can vary and you can choose whatever values you want to use. So with the cutoff frequencies chosen, I implemented a band pass filter. So the high pass cutoff frequency was set at 30 Hz and the low pass cutoff frequency at 300 Hz. I used a 4th order Butterworth bandpass filter. Of course, you can choose any order filter you want to use. So first the filter has to be created, and you can create the filter using the butter function on MATLAB. Specify the order, the cutoff frequencies, the Nyquist frequency, and the type of filter, which is bandpass. Following that, the filter can be applied to the dataset using the filt function on MATLAB. So let's go ahead and run this. So the filter has now been applied. The next step is rectification. So like I mentioned in my previous video, the raw signal has both positive and negative components, the average of which would be 0 because the positive and negative parts cancel each other out. Due to that, the result would be statistically insignificant. So the signal has to be rectified. And this is done by simply taking the absolute value of the signal. Right, so let's run that. And now we can plot the signal after it has been filtered and rectified, which is what I've done in this step. So I'll go ahead and run it. So this is what the filtered and rectified signal looks like. As you can see, there are only positive components. Right. So the next step is to find the RMS envelope, or a moving average, and this shows the mean power or the average power of the signal. I used a window size of 50 milliseconds. Of course, you are free to change this value in any way you like. A larger window size will encompass more of the original signal, but it would also have more distortion and be spiky. On the other hand, a lower window size would give a rather flat signal which does not reflect the peaks and the bumps of the original signal. So you have to choose a moderate window size. So over here the envelope is calculated. So a square root is taken. First the average using the move mean function, which is a moving average with respect to a window size. Before that, the rectified signal is squared and the final product undergoes a square root. So this is practically a root mean square. The next step, before I go there, I will run this. Right. So the final step is normalization. So if you want to compare your signal across different subjects, you have to normalize it. And this is normalized with respect to the maximum voluntary contraction, or MVC, which was discussed again in my previous video. So simply, I just divided the envelope against the MVC and obtained the final reading as a percentage. I will run. And finally, I plotted the normalized envelope against the rectified signal. I cropped the signal based on 2 randomly chosen limits, and it was cropped using the xlim function on MATLAB. This was done to get a zoomed up version of the signal. So I'll go ahead and run this. And this is the final output. So the blue signal is the rectified filtered signal, and the red line shows the normalized RMS envelope. So depending on the window size, as you can see, it encompasses most of the original signal, but not all of it. But it effectively reflects where the signal peaks up, such as in this area, and where it's low or flat, such as in this area. Alright guys, so that's all for this video. I hope you guys liked the video and enjoyed it. Now, if you guys haven't done so already, please give me a thumbs up by clicking the like button below. If you have any questions or clarifications on the code we just ran through for SEMG signals, please feel free to leave a comment and I will do my best to get back to you. So just to reiterate, I won't be sharing the code online, but if you want access to the code, you can leave a comment or email me and I can send the code to you. If you guys haven't done so already, please click that subscribe button. Thank you all for watching and I'll see you in the next video. Cheers.